But I'm just going to quickly then show you guys, since we have about 5 minutes before I have to head out. We could probably go a little bit longer, but I did want to share, I kind of took one of our other instructors, Jeff Herman. I don't know if you guys have bumped into him before. He created this nice little notebook. So I just kind of took this, kind of borrowed this from him and just kind of modified it a little bit and kind of show a little bit like how you would do gradient descent and what this looks like. So I'm just pulling in this data real quick. I'll just do it real quickly, but if you guys have questions, just stop me as you go through. And I'm just gonna, this is just some data, right? And I'm just gonna randomly pull, well, I'm gonna specifically choose like these two targets, or this feature and this target. So a very simple, you know, two-dimensional y equals mx plus b, with x being this gradient, I can't remember what this GR living area is, was actually represented. But you can see what this data looks like in 2 dimensions. You can see as we increase on the x value here, the target value here kind of increases, but we got some outliers as well. So I'm just going to quickly remove these. I already like looked at this ahead of time, right? So that's why I'm removing these specific outliers. I'm just moving these guys so it's a little bit easier for us to see. And now we can see it a little bit easier, so we're not having to worry about those weird outliers that are going to mess us up. And then, so I'm just going to define this regression formula. So this is like the thing that, this is the model that we're trying to optimize for. So this is why, for example, you can see I could just have X. I could have interacting features and stuff like this, or many, many features, but this is the model architecture that I'm going to go off of and define our cost function off of this guy and try to optimize for this specific model. Okay, so I'm just going to start off with a y-intercept of 0 and a slope of 0, which obviously is going to be a really bad model, right? And so I'm just going to plot this against here. And you can see here the data, and then the black line is my model. And you can see pretty bad model, and we can actually quantify it with the error. So you can just really quickly, I'm just adding up the total error here. And so what's nice is that I don't really care about it. In this case, I am squaring it. So like this is just the RSS. Yeah, I always mess it up. But the RSS, there we go. And you can see, I can actually see what the error is. Like, okay, that's pretty big, right? I mean, this is all relative, right? This could be fine, but you can probably guess this is a pretty bad model. So we want to get a better model. So we can use gradient descent, and basically gradient descent relies on taking the model itself. So you can see that is our model. Sorry, this is our model right here. This is our b plus, you know, a times xi. Well, in this case, xi is just going to be, you know, that first one. And we're going to square it against the predicted part right here, this yi, I'm sorry, the actual y, right? So this is going to be our prediction of with the x data point, and this y is going to be the actual level. We're going to square that. So that basically is our error term squared, right? And we're going to take the derivative of this thing. Well, since we already know what the form this takes, and it's going to be reliant on b, which is our parameter, right? It's our y-intercept. We're trying to optimize b. So we're taking the derivative of b. Basically, you can think of it like, I talked about like the bird boxing. It's like, do you take left and right? Left and right is our b, and then up and down is going to be like our a parameter, or slope. So I take derivative with respect to b, I get this value, or this equation right here. This is our gradient, for at least with respect to b, and this is going to be a right here. This is our gradient of a. And you can double check that, right? You can do like, you would figure out this derivative ahead of time. But now we actually know what this equation is. And what I can do now, I just went ahead and defined our partial derivative, so I don't have to literally type this equation out. I can just say partial derivative based on this equation. I'm just returning literally this guy right here. And then if it's a, returning, well, I should say, if I'm returning b, it's this guy. Otherwise, I'm returning this guy right here. Okay, that's what this is doing. Okay, so this makes it a little bit easier for us to write. And then I have a step gradient. So what I'm going to do is for every step I'm going to go, I'm going to take a jump forward in the direction that's going to basically the steepest direction. So whatever the steepest direction in A is, the steepest direction in B is, and then take a big leap forward. This is going to be scaled by learning rate. So this basically, your learning rate is saying how daring are you? Do you take a big leap forward, or do you take like a little leap forward? So you can imagine making a small learning rate. It's going to take us longer to go down the hill, but we're going to be more precise, and we're probably not going to overshoot. For example, if you have like a big old like divot here and you have a big jump, you might jump all the way over and skip the lowest point. Or if you take the little jumps, you would eventually hit the smallest point. So that's where that learning rate is coming from. And you can see here, that's what's going on here. I'm basically just taking the partial derivative, which we defined up here. And basically this is just using this -2 part just because we're always going to use it every single time. And I'm going to just divide it by n, so I'm going to divide the whole thing by n each time. This is pretty typical, just kind of making this equation. And we're just going to go through the whole thing. And then we can say, okay, the new B, the new place I'm going to jump to is going to be where I started off with. And then learning rate, how daring am I? Am I going to jump a big jump or a small jump times dB, which is basically what is the best direction to go in, you know, or like how big of a jump should I go in that direction? And so that helps us basically lower our time. So that way we're not always taking very iterative, the same amount of jumps. If it's very steep, I'm going to take a big jump. If it's not very steep, I'm going to take a little jump. Make sense? Cool. All right, everyone following me so far? And I'm kind of going through this pretty quickly.
I was gonna say it's a lot of custom functions. I was hoping there'd be something built in. Like
oh, yes. For the record, you will generally not be programming gradient descent by hand, but it's useful to see like how this works because in the end, like you should know how it works, so that way you know where you're tripping up and how you need to adjust your hyperparameters. For example, like I said, talk about the learning rate. If you are not getting to the answer very quickly, like you might need to adjust your alpha because you're not taking huge steps. But there's also things you can do. For example, like instead of taking big jumps every single time, you can say, well, as I get closer and closer to like the minimum point, I can take smaller and smaller jumps. So that's optimizing again for your learning rate and stuff like this. But if you just think of it as just a bunch of numbers that you can keep tuning, it's going to be difficult to like know why are you turning this value. It's like people used to say like, oh, what alpha value should I use? And they just randomly just put the number in there because they're like, I don't know what's happening. Just try it enough times and eventually something happens. That's kind of what we're trying to like prevent. But in reality, you probably wouldn't be making these functions yourself. But I think it's useful as like, it's kind of like saying your math teacher's like, hey, remember, this is the really hard way of doing something. And now here's the easy way. But if you know the hard way, at least now you say, oh, when I'm doing this easy way, I know why this is working. So if I come across an issue, I can go back to the hard way or know how the hard way works to adjust this a little bit. I'm a little bit over time. Are you guys okay if I keep kind of going through? Like, no hard feelings if you guys have to head out. I know it can be kind of late for you guys. Okay, cool, I'll keep going. But anyway, yeah, this gradient descent. I just have this definition and it's like, okay, cool, we got these functions done. Now I can actually do just the part. So basically each time I do this, I'm just going to use my step or my gradient, do a step in that certain direction, that jump, right? And then I'm going to have a new values for my, I think I put it, what is it? A or VA. So my slope, oh, sorry, my intercept and my slope. So these are my new values for my intercept and my slope based on the gradient on here. And if I actually plot this out, you will see it is really bad still. In fact, you can see all the data points that originally looked like this. It's so far off, it's really small. And that's because I took a huge jump because my, I didn't change my learning rate. My learning rate basically was 0.1, so it's pretty big. And so I'm gonna readjust this to a smaller learning rate. You can see my error is really bad, but I can actually change like, okay, like let's check out, you can see, yeah, here's my original guy and here's my, my big step, like huge error. So I can actually change my learning rate to very, very small. So I take a very modest jump versus taking a very small, very big jump. And if I do this now, you can say, hey, that's not bad. And in fact, if I go and plot this out, you should now see that's a lot better. So you can see originally I was like really flat and now I'm a little bit up higher. So this learning rate could be maybe adjusted, like maybe, let's see if I did that. You can see, yeah, I could still overjumped it, but not too bad, right? So this is where that learning rate just depends on what's gonna happen. So like, I'm gonna keep it at this learning rate right here. So you can see I jumped up, but I'm still not the best. So I'm gonna keep moving across that cost function, trying to increase it better. But instead of going little by little by little by little, I'm just gonna kind of keep jumping across and see if I can get to the better option. So my second step, and this is where I'm just gonna kind of go through. You can see I do a second step and then my third step. So all I'm doing is basically, I could have put this in a for loop and you could see I would just get better and better a little bit, okay? And so let's just go ahead and just do multiple iterations. I'm gonna run this through. So this is basically doing it 100 times, exactly what I'm doing. So this is if I just did a for loop and just iterated over and over and over and over again. And we can see how our errors change. And hope it should be, our gradient descent should be getting smaller and smaller errors. Okay, and you can see here, there it is. Like we can start off with a very big error and we get smaller and smaller and smaller until basically we're pretty much at the best point we can possibly be. So you can see that we get really good. If I wanted to show this here, oh, yeah, so it looks like, so one thing I found notes here is like, we could have stopped like probably right here. That's pretty good. Like we didn't have to go that much better, but we wasted a whole bunch of time. So we could actually stop it when it gets to a point where it's like, hey, your error is not really changing that much. So this is called early stopping. So basically I added this extra part right here where if the error is basically not a 1% difference, so basically your 1% difference doesn't change, we stop it. So it stops at the 47th step. So it'd stop right about like here. Basically the error is not changing that much. So we should just stop. Like, we don't need to waste all this extra time. And so again, we can see this plot. It should look the same thing, but you can see we stopped before it started getting into that flat line or not changing too much. Does that make sense to people? Like what I did here? Okay, so not, it's cool. All right, and this is what you'd ideally want to have ahead of time. You wouldn't want to look at this and then say, oh, I should do early stopping. So again, these are kind of like, you'll see early stopping as an option in like when you actually use a library that does this automatically. So now it's like, okay, cool. Let's go ahead then and actually plot out these different parts. So basically every 10 iterations, I'm just going to plot out the difference. So you can see here, here's the error graph. You can see it for every 10 iterations. And you can see on this left here, how the model's getting better and better. And it's just using gradient descent, basically saying, okay, what direction do I go in? And you can see it's getting better and better. And you can see it's getting at the 30 or the 50 mark, at the 60 mark right here. It's technically getting better and better, but it's probably not moving very much as we go further and further along, as we saw. Like the error hasn't changed that much. So, and there's my model, the best I have at least for the errors. Note that it's probably a little skewed off to the right here because there's so many values over here. Okay, cool. Does everyone understand like this iteration looking pretty good? Cool. All right, and so then you're like, okay, well that was a lot pain in the butt, right? Like I just wrote all these special functions, stuff like this, and then you say, hey, let's not do that. Let's use someone else. Let's use what someone else did with optimization stuff. So I'm using sklearn's linear model, linear regression. You guys probably saw linear regression, and I can actually go ahead and say, okay, I'm going to define linear regression. I'm going to fit these values. Note I'm just reshaping them so they can actually use a dot fit. And what that dot fit basically is that it's going to say, hey, just use gradient descent to go ahead and figure this out. And you can see the coefficients. I never pulled up the coefficients, but it should hopefully show you what the best intercept and what the best, this is, I think this is our linear, this is our slope, and I think this is our y-intercept right here. And so if I look at my MB that we determined, we should get something pretty close. We should see, hey, that's pretty close for designing our own thing, 118 and 0.72. Well, okay, y-intercept's not that close, but also we might not matter that much. Like this actually might not be as big of an issue, but I don't know. Let's see here. And just plotting it out, you can kind of see the one that we use for our gradient descent, this guy right here, y-intercept's like, oh yeah, you can see it kind of like, you can see the fact, I think this B must be wrong, actually. I don't know. Yeah, this is probably wrong. I have to figure out where I changed the B, but whatever we use for gradient descent, no, that's why our B is fine. Okay, maybe it's, oh, you know what? It's so, that's the thing, that this guy right here is such insufficient, like insignificant. Like I was so far off on the B, it was good enough. So maybe if I iterated it even longer, maybe eventually I'd get a better B. I don't know. But you can see basically pretty much spot on, like close to it. I think, yeah, I can see like, why did my B go weird? But you can see the square root error for my model, error for linear regression, which I think might be actually a little bit bigger. And then we can actually see again for MB. I think I'm just kind of playing around with it. Oh, I'm taking the square root, that's why. Because it's total error.
For that linear regression class, do you, is there arguments built in for like the learning rate and the stop and all that?
Yeah, so it actually turns out it's not on the linear regression, it's actually on the fit. So we can actually define how we do this fit, if I remember this right. Let's see here. Visual weights for each sample. I'd have to look at the documentation to be sure.
Oh,
but
okay. Probably on the fit somewhere.
Yeah, like it's the way it's defined for linear regression for that thing. It's going to say how does it actually do a fit. So that would be like where you'd want to explore. But yeah, so anyway, like you can see, like I didn't have to do it myself. Like you can just use sklearn, right, to do it for you. And the really cool thing is that once you just understand, like, oh, I can do a dot fit, and you know it's using gradient descent, you can actually put in whatever machine learning algorithm you have on here, and sklearn basically has the same dot fit function. So you don't have to do a huge amount of changes.
How big does this data set have to get until I have to start putting those arguments in?
Like which arguments? Like
yeah, just like the learning rate and the stop of.
Yeah, it's going to be most important. So linear regression is solved pretty quickly because you're just drawing a line and you just kind of iterate on top of it, but it's not going to be super complex. When it really matters is when you have other machine learning models. I'm trying to remember what the first one you guys learn. I know you guys do logistic regression, which is just linear regression, but
Like random forest.
Random forest. Okay, yeah. So random forest is going to. Oh, that's actually might probably decision tree is probably closer to what you guys would first kind of consider. That's going to basically try to iterate and try to find the parameters, but the parameters are going to be defined by the cost function. And so it's going to iterate many, many, many times over. And so like this thing, like for example, you can see how quickly this took. This took like less than a second, like 0.2 seconds. For other models, you might literally have something go on for, you know, like you'd probably see something closer to like 8 seconds, depending how big the data set is. Like by big, I mean like, oh, like 100,000 data points. Like that's actually relatively small, but big enough where you start seeing that difference. And then for certain models, you might actually see literally like hours. Like for example, neural networks famously take hours, if not days, if not weeks, to basically train over and over again. And it's using the same process of gradient descent. It's just that it's going to, the thing that's going to change is the cost function, and then therefore the derivative is going to be the thing that's going to change for each linear model. But the concept is still the same thing. Make sense?
Yeah. I'm just curious, like what's simulating for a week versus 3 milliseconds? Like what are the parameter, like what are the variables that are being simulated in the combination? Like I assume the combination goes into it. I get that. What's being simulated for that long?
Yeah, it's not simulated. It's that, so if you saw how quickly, like, for example, if you look at how quickly this took, let's see if I go up here. You can see this took 20 seconds. And I'm doing linear regression here. So you can see I'm actually doing the same exact thing sklearn does, right? But you can see how quickly, like I didn't optimize at all. I was doing really like, so it's like, oh, proof of concept, here's gradient descent, here's partial derivative, you know, for a very simple model. And it took me 20 seconds for me to iterate on top of this. It's going to depend on what is optimized for that package, if that makes sense. And so sklearn in particular is using NumPy's connection to basically the underlying C for Python, which is going to make this super fast. All the stuff I showed you before this point with sklearn is like not optimized at all. It's super slow. Like you can see 20 seconds is ridiculously slow compared to doing the same exact process that took like 20 seconds for sklearn. And that's because it's optimized for what it's supposed to be done. I couldn't give you an exact value of like where you'd start seeing this the most, but as you get into like 100,000, you know, 500,000, like that range, you'll start seeing it significantly like, okay, it's no longer taking like less than a second. It might take longer. And then just the number of features. And then it's also going to depend on what model architecture you have. This is when it starts getting into very much like a lot of dials and stuff of being like, what's going to make the most sense for this model. For example, a neural network, if you never do any feature engineering on a neural network, your neural network might take a really, really long time to optimize. Where linear regression, really it's going to be really quick to like draw out this model. But the advantage of a neural network versus linear regression is that you can make it a lot more complex, which means that you can get higher accuracies. You have to be careful of overfitting, but you can get a better model essentially. And linear regression is just like more difficult to actually pull up, what's it called? Like pull up these more complex factors because you have to spend so much time on designing the architecture, essentially the linear model equation. Hopefully that makes sense. Yeah, okay. Hopefully, I think it makes more sense when you start looking at how other machine learning models like decision trees, where you aren't just saying how you define the decision tree, you're just saying where does it split off. I know you guys haven't gotten to this point yet. You guys will get into the next couple weeks, I think. But decision tree is random forest, where basically you define the hyperparameters, which is like, okay, when does this split off, you know? And that's built into the cost function itself. So you don't actually have to define, well, okay, like how many layers does this decision tree have to have? The machine learning model or algorithm uses that as a factor and can optimize across there. So one thing, for example, like if I really wanted to optimize this, like, linear regression, I should have some parameter that also controls how many polynomial, variables do I use? What features are kind of put into this model? And obviously that's not in there because I have to define those myself. I have to say, hey, is it worth me putting interacting features, polynomial features, and all that stuff? And that's the thing that's going to take more time, right? You have to investigate and see, is it a significant value, the p-values and stuff. Where with machine learning models, like you actually, if you look up like people, like textbooks and stuff like that talk about machine learning, they'll talk about linear regression. They never show p-values, which is what you should be talking about, like, when you technically do linear regression. And it's because machine learning algorithms, they don't have that same concept because essentially you're optimizing on the parameters itself. Hopefully that makes sense without me. Like, obviously, all you guys know is linear regression right now, really, from like the curriculum.
I noticed that like applying the right polynomial regression on like a certain feature, like it works. Like it does raise the value if you can find it, but it takes time.
Yeah, exactly. Like you have to figure out like you either have to try a bunch of different things, right, which takes time, or you know something inherently about the system itself as a person. Like, conceptually, oh, this should be interacting with itself. Let me throw that in there and see if that works well. But that also takes cognitive work on you, right? You have to figure out what's the best thing. And linear regression is not really optimized for you just to throw, what's it called? Like just throw things at it and see how well it does, because it takes a long time as you add more and more features into it.
I love it. Yeah, I was worried about that because I was thinking to myself, like, am I just going to keep guessing? Like, how is this going to work? And it kind of answers the question. Like, no, you don't really have to guess. These things are built in. That's huge.
Yeah, good. But yeah, hopefully you guys will see too. Like, you're like, oh wow, this makes a lot. Like, it's almost sometimes hard to go back to linear regression when you're doing machine learning models, because it's just like, oh, like there's so much more. It's a different kind of work, if that makes sense. There's still work for machine learning models, but it's a different kind of like thinking, where you're thinking of how to optimize to learn it.
You're learning, investigating like a new concept almost. Like, it's not like you're just guessing at something.
Yeah, in some ways you might be guessing at some level, but it's more like, instead of design, it's almost like saying, instead of like designing the perfect test taker with machine learning models, like with gradient descent, you instead are designing the perfect classroom to create the best test taker. So linear regression is like you're designing the best test taker and like saying what you should do. And in machine learning models, like with gradient descent, that kind of stuff, you're designing the classroom to say, hey, what's the best way for you to learn to get the best test taker?
It's a good analogy.
Yeah.
Okay. You're saying make it over fit, right?
Yeah, and that's the problem too, is like you want to make sure your classroom is designed in such a way that your little student, right, your machine learning algorithm is doing a good job of actually generalizing well, like actually learning, right, versus just memorizing answers. Like a good, you might say like a good student, you just give them the answers to tests. Well, obviously that's not going to do a very good job generalizing very well, but you can design a classroom in that way too, where maybe it's encouraged to do those things. I'm getting very like metaphorical like at this point. I think it's helpful sometimes a little less. Yeah.